Welcome, focused learners, to this explainer. Listen, if you're looking to truly master Cambridge electrical physics, you are in the exact right place. Today, we're taking a completely different approach. We're going to treat your brain like a machine that we are going to program for absolute efficiency. Think of this as the robot engineer mindset. We aren't just going to look at the raw theory today, we are going to build a highly structured concept-to-application blueprint specifically designed for Cambridge syllabus codes like 0625, 0651, 0652, 5054, and 9702. Now, to kick things off, I want you to imagine two completely different students taking the exact same past paper. Let's call them Alex and Sam. When Alex sees an electrical circuit question, he completely overloads. He dumps every single raw physics fact he's ever memorized onto the page, but with absolutely zero analysis. He writes a novel, and he runs out of time. Sam, on the other hand? Sam rushes. Sam looks at the question, completely misses the specific command word requirements, does a quick calculation, forgets the units, and leaves half the marks on the table. If we were looking at their exams side by side right now, they'd just be covered in red pen marks. Good effort. Terrible strategy. By the time we finish today, you'll not only understand the fundamental behaviors of electrical quantities, but you will have the automated patterns needed to avoid being an Alex or a Sam. You're going to know exactly how to translate your knowledge into maximum, guaranteed marks. Okay, let's dive into this.
Here is our blueprint for today's session. First, the flow and the push, getting into the realities of current. Second, voltage, EMF, and work. Third, resistance and power. And finally, Section 4, mastering exam command words. This last section is absolutely crucial, folks. It's the secret sauce that takes you from a C grade to an A star. Let's get right into it.
Section 1, the flow and the push. This is the bedrock of everything electricity related.
Okay, what we have right here brilliantly illustrates the bridge between physical reality and exam theory. On the left side, we have a literal laboratory setup, a cell, a switch, and a filament lamp connected by middle wires. On the right, we have the exact same circuit represented as a standard circuit diagram. Now, this is exactly where someone like Alex starts overcomplicating things, but the examiner just wants you to recognize the standard symbols. Notice that cell symbol on the right? See that longer vertical line? That represents the positive terminal. By absolute convention, whenever we draw our current arrows, they must flow from that positive, longer line all the way around the circuit and back to the shorter negative line. This is what we call conventional current. If you draw your arrows the other way in an exam, the examiner will immediately reach for that red pen.
But here is where we really need to be precise, and where top-tier students separate themselves from the pack. The formal definition of current is the rate at which electric charge passes a point in a circuit. However, while our conventional current arrows point from positive to negative, the actual physical reality happening inside those metal wires is quite different. The current is actually a physical flow of negatively charged electrons. And because they are negatively charged, they are strongly repelled by the negative terminal and attracted toward the positive one. So in reality, electrons are flowing in the exact opposite direction of conventional current. It's a bit of a historical quirk, really. The pioneers of electricity guessed the direction of flow before they actually discovered the electron. Just keep that distinction locked in your mind. Conventional current flows positive to negative, but the actual electrons flow negative to positive.
To master the math of this flow, you absolutely must understand how these core quantities interrelate. Current, which is given the symbol I and measured in amps, is charge, symbol Q, measured in coulombs, divided by time, measured strictly in seconds. Before we continue breaking down this math, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. All right, let's make this formula tangible so you never forget it. If an exam question tells you a circuit has a current of 10 amps, what does that actually mean? It means exactly 10 coulombs of charge are physically flowing past a specific point in that circuit every single second. 10 chunks of charge every second. Memorize this foundational relationship. Charge equals current times time, or Q equals I times T. When Sam rushes through an exam, he often divides when he should multiply, or he forgets that time must be in seconds. Don't be like Sam. Program this pattern into your brain.
Section 2, voltage, EMF, and work. Now we move from the flow of the charge to the actual push behind it.
Take a really close look at this circuit setup. We have a cell doing the work, pushing current through a resistor. But look specifically at how the voltmeter is connected. Unlike an ammeter, which sits in series right in the main path to count the flow of charge, a voltmeter must always be connected in parallel. It sits across the component in its own little separate branch. Why? because it's measuring a difference in potential between two specific points. It's looking at the energy the charge has before it enters the resistor and comparing it to the energy it has after it leaves. Alex might write a whole paragraph about the internal workings of the meter here, but the automated, correct response is simply, a voltmeter is connected in parallel to measure potential difference. Keep it crisp.
Now let's tackle what is arguably the biggest terminology trap in the entire Cambridge physics syllabus: EMF versus PD. They are both voltages, yes, but they describe entirely different things. Electromotive force, or EMF, is the electrical work done by a source, like a battery or a generator, in moving a unit charge entirely around the complete circuit. It is the total energy supplied to the system. And listen, the name itself is a trap. It is a voltage. It is not a physical force measured in newtons. On the other hand, potential difference, or PD, is the work done by that charge passing through a specific component, transferring its energy to, say, light up a lamp or heat up a resistor. Think of it like a financial budget. EMF is the total paycheck you receive for the month. Potential difference is how you spend that paycheck at specific stores. EMF is the total budget provided. PD is how it's spent at a specific location. If an exam asks you to distinguish between the two, this is where you use our physics success blueprint. Your point is the definition. Your evidence is the total circuit versus the specific component. That turns a red pen mark into a green check mark every single time.
Both EMF and PDR are measured in volts. But what actually is a volt? The definition is incredibly elegant, and examiners love to test it. 1 volt equals 1 joule of work done per coulomb of charge. Think of it exactly like this. If you plug a device into a standard 230 volts mains supply, that supply is doing exactly 230 joules of work on every single coulomb of charge it pushes around the circuit. It's simply an energy-to-charge ratio. 1V equals 1 joule over C. If you can remember that a volt is just a joule per coulomb, you can derive half the equations in this unit without even trying.
Section 3, Resistance and Power. This is where we look at the obstacles in our circuit and how energy is ultimately consumed. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, back to the physics. As charge flows through a wire, it doesn't get a free ride. It encounters resistance, measured in ohms. It's exactly what it sounds like, a measure of how difficult it is for the electric current to flow. Mathematically, the resistance is defined as the potential difference across the component divided by the current passing through it. R equals V divided by I. If you add more components to a simple series circuit, you are actively increasing the overall electrical resistance. Because the battery's push, its EMF, is fixed, a higher resistance means a smaller current will flow. It is a direct, unavoidable trade-off. Let's do a quick data scan challenge right now. If I double the resistance in a circuit, but keep the voltage exactly the same, what happens to the current? 3, 2, 1. It halves. If you saw that instantly, your brain is starting to automate these relationships.
So how do we use this to calculate actual energy usage? Electrical power is simply the rate at which energy is transferred, calculated as current times voltage, or P equals IV. Power is measured in watts, where 1 watt is exactly 1 joule per second. If you want to know the total energy transferred, you just multiply that power by the time the circuit is actually running. That gives us E equals IVT. Now, let's do a find the flaw challenge. Imagine Sam writes this in his exam. To find the energy of a heater running at 5 amps and 20 volts for 3 minutes, I calculated 5 times 20 times 3, which equals 300 joules. Did you spot the fatal flaw? Sam forgot the golden rule. Time must always be converted into seconds for the E equals IVT equation to work. 3 minutes is 180 seconds. The calculation should be 5 times 20 times 180. If an exam question says 3 minutes, your immediate automated robot response must be to cross that out and write 180 seconds on the paper before you even touch your calculator.
Section 4, Mastering Exam Command Words. We covered the physics. Now we cover how to actually extract the marks from the examiner.
Cambridge exams are incredibly specific about what they want, and it all hinges on the command word they use. This is where we introduce the PEEL framework: point, evidence, explanation, link. But you only use it when required. If a question asks you to state, they just want the clear factor formula. No essays, no PEEL framework required. Calculate means you have to crunch the numbers provided and show you're working.
Give means pluck the answer right off a graph or from your memory. But explain? Ah, that's the heavy lifter. You cannot just give a fact for an explain question. You must set out the reasons and provide supporting evidence. Writing a massive paragraph when asked to simply state something is exactly what Alex does, and it wastes valuable exam time. Giving a one-word answer when asked to explain is what Sam does, and it loses massive marks.
Here is a brilliant example of a high-pressure exam question, a lightning strike scenario. Part A asks you to state the relationship between distance, speed, and time. Let's do a speed writing challenge. You have 10 seconds. Notice it doesn't ask how they are related in nature, just the relationship. You literally just write speed equals distance divided by time. Done. 1 mark secured. But Part B says calculate the time it takes. Now you have to shift gears. You must plug the given 5 kilometers and the speed of light into that formula. Later in the same question, it might ask you to calculate energy using a 30 kiloamp current and a 33 megavolt potential difference. You have to be totally comfortable converting those prefixes, kilo into thousands, mega into millions, into standard units before you even start calculating. State is quick, calculate requires precision.
Let's look at one final critical example to solidify our system. Here is a classic IV characteristic graph for a filament lamp. Part I asks you to use the graph to find. This is essentially a give command. You just read the value right off the axis. Easy. But look at part IV. Explain the shape of the IV characteristic. This is worth 2, maybe 3 marks. Alex might write a page about the history of light bulbs. Sam might just write, it curves because it gets hot. Both fail. To satisfy the explain command, we use our framework. Point. The graph curves because resistance is not constant. Evidence. As current increases, the temperature of the filament physically increases. Explanation. This higher temperature causes the metal ions to vibrate more, which increases the resistance to the electron flow, resulting in the curve we see flattening out. You have to connect the dots for the examiner. That is the 3-rule system. Decode the command word, apply the Peel framework for explanations, and manage your time matrix by not overwriting simple state questions. Mastering these details, from the physical flow of electrons to decoding the exact phrasing of an exam question, is what transforms a good student into an absolute grade A machine. To wrap up our explainer today, I want to leave you with a provocative thought. Try describing our world if electricity had not been discovered. Think about the automated power, the massive data centers, the sheer energy transfer we've just learned how to calculate. Our entire modern existence hinges on mastering the simple yet profound relationship between voltage, current, and resistance. Students who implement these physics strategies see an average improvement of 2 full grade boundaries. But that only happens if they practice consistently with our weekly videos. So here's your final reminder. Subscribe to our YouTube channel Ace the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Before you go, drop a comment below with your target grade for physics and the biggest challenge you're currently facing. Our team actively responds to every single comment. Like and share this video with a study partner who needs a wake-up call. Ace the Exams. Your Cambridge success starts here. Keep practicing those equations, respect those command words, and keep learning.